will record this lecture. It's recording on Learning Suite, or I'm sorry, on Zoom as well. And so you'll be able to review these notes afterwards in both video form, and then I'll post them as PDFs. All right, so the standing wave, we think about an axis. You've got a couple of interesting features. You've got crests and troughs, and then you have these positions where the wave goes to zero, and we're going to call that a node, all right? Similarly, electron wave functions that you should have learned about in the introductory study guide have some of these same properties. Wave functions describe the wave-like properties of an electron. They have an amplitude. That amplitude can have a positive sign or a negative sign, and they can go through zero. They can have an amplitude of zero at certain locations in space. For example, second row elements have a couple of different wave functions available to them, and that's summarized in the introductory study guide. They have a 2s wave function, and it consists of two concentric spheres. There's an inner sphere and an outer sphere, and there's a node surface, spherical node surface in between those two spheres where the wave function goes to zero, and the sign of the wave function is different inside than it is outside. So we're going to use color to represent wave function sign in most cases. And I have to be careful to try to use red, green, colorblind friendly colors, and I will fail most of the time, and this starts looking like the evil eye of Sauron or something. Sorry. The node becomes more visible in a 2p orbital, so we'll use shading to indicate that the wave function has opposite signs on either side of this node. The node is this plane that's sort of perpendicular to that 2p orbital lobe. Now you must think of the electron as occupying all of that area simultaneously. It's not like it's a little dot floating around jumping magically from one side to the other. It is that space. It occupies that space. All right, so that's just a crash course in wave functions and orbitals. We now want to talk about molecules. One of the great things about waves is they can superimpose with each other. They can interact via constructive interference or destructive interference. So let's think about constructive interference with waves. This is where you have a waveform that looks like this, and probably should have just copied the PowerPoint slide instead of tried to do that. And let's say it's propagating in this direction with time. Let's suppose we take another wave and add it through at exactly the same time and location, only I guess to indicate that these are two different waves, we might make it a different color, who knows. Okay, what happens with waves, if you've taken some physics or just intuitively, what's going to happen when I add these two waves together precisely in phase? And what I mean by in phase is all of the crests are lined up, all of the troughs are lined up, all of the nodes are lined up. Okay, so what should happen? Go ahead.
The amplitude of the wave should increase.
Yeah, it's just simple addition, right? The amplitude of the wave increases, so here's our pink axis of propagation, and then we would expect, I'm going to cheat, and I'm going to do something that you guys can't do. Well, will it stretch in that? No. Okay, I'm not actually going to cheat. Sometimes I will use this app to do copy and paste and annoying things like that that tend to get you guys anxious because you're worried about copying it all down. In any case, you get the point, right? Yup. Constructive interference, the amplitudes add. Now let's do the exact opposite. Let's try to bring these waves together precisely out of phase. What we mean by that, we would call this destructive interference. What we mean by that is that the crests are in one wave are where the troughs are in the other wave. The nodes all line up. If I were to add these two waves together, what should I get? Nothing, right? Zero. Cancels it out. They cancel each other out. And in fact, you have to be careful with this kind of thing if you're dealing with acoustics in a large room, because sometimes the placement of speakers creates nodes or soft spots actually in the room where some of the waves are canceling each other out. All right. Well, electron wave functions can have similar properties. And the ability for wave functions to interfere with each other constructively or destructively is critical to understanding bonding in organic molecules. So we're going to start with the simplest possible organic molecule. And it's sort of an honorary organic molecule because it doesn't have carbon in it. But carbon and hydrogen are sort of the fundamental building blocks of organic molecules, so we'll say hydrogen's an honorary carbon and just include it on the list. Organic chemists are kind of snooty, by the way. We will say that anything that's not carbon or hydrogen, we're going to call heteroatoms, just the others. Okay? You have carbon, hydrogen, and then you have the others. But we're not angry at the others, the heteroatoms, because they're what actually bring cool function and reactivity to organic molecules. So let's think about how you make a covalent bond in hydrogen. In general chemistry, you were told, oh, well, they get to share electrons such that they each have noble gas configuration. Yay. That's fun, but electrons don't know that they have noble gas configuration, nor do they know why that should be appealing. We're going to see that the reason bonds form between atoms is because it allows their electrons to move to a lower energy level, period. So let's show how that can be. In the process of making this molecule and using the wave functions for the individual hydrogen atoms, what we're going to do is take the 1s orbital from one hydrogen atom and the 1s orbital from the other hydrogen atom, and we're going to bring them together constructively, that is, we'll add them together, and then we'll bring them together destructively, that is, we'll subtract one from the other. Now remember, the wave function can have positive mathematical sign or negative mathematical sign. We don't want to get confused with charge because there's pluses and minuses in charge in terms of organic chemistry. So to avoid that, we're simply going to use color to indicate that two different parts of a wave function have opposite mathematical sign. We will see that when we bring together two parts of the hydrogen wave function and they have opposite sign, they will cancel each other out at that location, and we'll have what's called a node. So let's think about the constructive interference or addition of we'll call this hydrogen hydrogen A, this one hydrogen B, the 1s orbital from hydrogen A with the 1s orbital from hydrogen B. What should that look like? Well, you've been taught that the 1s orbital looks like a sphere. When we draw an orbital, what we're really drawing is the square of the wave function, which gives you the probability of finding the electron within a certain at a certain location or within a certain area of space. This sphere captures all the points where the probability of finding an electron within that sphere is like greater than 95% or something like that. If we were then to bring another 1s wave function together, what would we see? They would begin to overlap in phase, and you would have a favorable bonding interaction. If this doesn't necessarily make sense, we can do it a little bit more quantitatively. I'm going to have a graph here where the y-axis is amplitude, and the x-axis is some distance. At this point, we're going to have the hydrogen atom A, and at this point, we're going to have the hydrogen atom B. And basically, we are scanning along along this distance outside the space between the two nuclei, in this space here, and then beyond, and we're measuring the amplitude of the wave function at those positions. If we did that, we would see that if we were to think about just the 1s orbital from hydrogen A on its own, what we would see would look something like this. And it would have a peak at the hydrogen, and then it would tail off and approach infinity the further away you got from that hydrogen A. So that's just in the world where hydrogen A is by itself. That's the wave function it would have. Let's use a different color for the same thing for hydrogen B. Again, we'd have a peak at the nucleus, and it would tail off to similar amounts in both directions as you approach infinity. Now, the amplitudes are the same, so what do you suppose happens if I mathematically combine those two wave functions together? What should I get? At each point, right, I'm going to add this number to that number, and that should get me something that is a little bit higher here, a little bit higher there, and then tails off, right? But in the middle, and maybe I've overdone it, I don't know. In the middle, we end up with a higher amplitude than we had before for either of the two s orbitals on their own, okay? There's some nuance here in terms of normalizing the orbitals, so the probability for both of them in all areas of the universe is 1, but we won't worry about that. So we can see that by adding these two orbitals together, we can get a new molecular orbital. But let's talk about the features of this molecular orbital. Remember, amplitude, if you square it, it gives you an idea of electron density. So what would you say about the electron density in this, what we're going to call 1sa plus 1sb orbital? Where is it mostly? Relative to the two atoms. Is it outside the area between them, or is it inside that area? Where do the electrons spend most of their time? Right, in this area here, right? And you can think about it as though those two electrons spending their time in that area are sort of pulling the two nuclei together. That's sort of an electrostatic or Coulombic argument. One of the reasons for bonding is because protons, positively charged protons, are attracted to negatively charged electrons. But there's another interesting feature here, and that is the fact that the energy of a wave function is described by the Schrodinger equation, which is described in more detail in that introductory study guide. You have an operator called the Hamiltonian, which is a function that if you apply to the wave function, it returns the wave function itself unmodified except by a constant, and in the case of the Hamiltonian operator, that constant is the energy. I remember seeing that equation in undergraduate Gen Chem and thinking, what does that tell me? H strange Greek letter equals E strange Greek letter. That is not very useful. How profound is that? It turns out you can learn a little bit more if you get inside what the Hamiltonian operator is. The Hamiltonian describes the kinetic energy is a function that if you multiply it by, if you apply it to the wave function, it gives you the wave function's energy. So the Hamiltonian has terms for both kinetic energy and potential energy, because those are the two kinds of energy we have, right? Potential energy of the electron is simply related to Coulomb's law. Negative charges attract positive charges. Not a huge deal, or rather easy to understand. Kinetic energy of the electron is a little bit trickier, and so I'm not going to derive this in class. I'll refer you to the introductory study guide. But the kinetic energy operator is opposite of h bar, which is Planck's constant divided by 2 pi. Now that I've made a big deal out of it, I'm afraid I'm going to get it wrong, so I'm going to look it up too. Over 2 times the mass of the electron times the second derivative of the electron with respect to, the second derivative of the wave function with respect to space. Because electrons exist in 3 spatial dimensions, we'll also represent this for the first and maybe last time with this del operator, which just tells you second derivative of the wave function over all space. Yes? Oh, that thing is in the way. Thank you for reminding me, and in the future, yeah, please tell me to get that stupid thing out of the way. Sorry about that. Okay. What this tells you is the second derivative of the wave function gives you some information about its kinetic energy, or the kinetic energy of an electron that has that wave function. Well, let's remind ourselves, I mean, this is a long time ago now, and this is maybe the only calculus you'll need in this class. For the rest of the class, if you can count and if you can divide by 2, you're usually okay. First derivative of a function is its slope, right? Second derivative of a function is what? Go ahead. Acceleration, good, which is the slope of the slope, or how the slope is changing, right? Some people talk about curvature. All right, let's look at, and I want you to compare how the slope is changing for just the 1s orbital by itself versus the new orbital that we got by adding the 1sa orbital to the 1sb orbital. Okay? Where is the slope changing, or in which of those two options, the red line or the black line, is the slope changing most? Some of you are worried that there might be a discontinuity at that point, and therefore these things might be undifferentiable. I don't care. We're not going to. I don't even know the answer to that, so we're not going to worry about that. 2 red or black lines, which one is the slope changing fastest in? Obviously, black wasn't the answer that I was looking for. Okay, let's think through this. So, red line, there's not a lot of difference in how the slope is changing for black versus red here, right? It's sort of the same. How about here? Seems like the slope bottoms out. The slope doesn't change as much. It gets to this point and it stops changing quite a bit, and then it eventually doesn't change much at all for a little bit and then starts changing again, whereas the rate of change here decreases. Let me try to draw a more realistic picture of what this new wave function would actually look like. That may be clearer. Now can you choose one where the slope is changing least? Okay, let me ask that a different way. Which of you don't believe that the slope is changing slowly here? Yeah, that's a great comment. And the comment was that it seems like going from a higher slope here to here may be a bigger change than just going from here to here. And it's not a perfect comparison. The kinetic energy of an electron isn't something you can calculate at a single point. It's something that the electron has in a whole orbital, and so we'd really have to calculate it for the entire function itself. At least in this section between the two atoms, that's sort of a shallower dip than here for the red function. Can you see that? In this region between the two atoms, the slope is changing. I don't know, am I wrong? Go ahead.
I think it depends on how steep it is right after the peak.
Okay.
Because if your slope is at like -5 right after the peak and it goes to 0, then you fall from -1 to 1.
Okay. Yes, I think you're right, and some of this might.
I needed numbers.
No, I appreciate that a lot. I'm trying to. I wonder if it might help to. Let's see. Go to Dropbox, and I'll show you the actual graph because I think my drawing is inhibiting the stuff here. Let's see. Files. Wait, maybe. Oh, there it is. Look at those nice drawings. I shouldn't have tried. Okay, there's the graph. Can you see that I was talking about? There's a lot of lines going on here. Oops. The large dashes are the wave function for this hydrogen atom. The dot dash 1 is the wave function for hydrogen B. In red is the sum of those two. Why isn't it double the height of the peak, or why isn't it at least higher? It has to do with the fact that wave functions are always normalized so that the integral over all space is equal to 1. Probability can't go to 200, so even though you're adding these two things together, you have to renormalize it. Don't worry about it that much. And then in the other dot dash is sort of the opposite of the wave function for hydrogen B, which just shows you that if you add this one to that one, you get a node in the middle. But just right now, compare the red line to the solid dash 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 line, and you can see the slope changes more abruptly for the 1s orbital than it does for the 1s plus 1s orbital. Saw a hand? No? Yeah. You are exactly right. So here is the cursor. The slope changes more abruptly for the 1s orbital on its own. You go from a fairly high positive number to a fairly high negative number, whereas you go from a slightly less high positive number to a slightly less high negative number. And I think the problem that we had there is that I wasn't necessarily showing you the normalized wave function, which doesn't make any sense. And if you want to know more about that, I can tell you more about it. But the point is that in this orbital where we've added the two wave functions together, the slope doesn't change as rapidly, and therefore the electron has lower kinetic energy. It slows down. And if your overall energy is potential plus kinetic, and you're an electron and you get to be between two nuclei, you get to experience two positive charges instead of just one, and you get to slow down, that's moving to a lower energy level. Okay? And so we'll see that by bringing these two wave functions together and adding them together, if this is the energy level of our starting 1s orbitals, if we add them together, their energy actually goes down. And this is why hydrogen forms, because if you have a single hydrogen atom with one electron here and a single hydrogen atom with one electron there, it's going to be more favorable for those wave functions to add together so that the electrons can move lower in energy. Yes?
So the less change that happens at the peak indicates also the less energy.
Yeah, the less change that happens, the smoother the slope, the shallower the slope. Because it's based on the second derivative. Yeah. And maybe we can illustrate this principle by thinking about the other thing that's got to happen. In the math of MO theory molecular orbital theory makes it so that if you consider adding two wave functions together, you must also consider subtracting one from the other. I don't have a good explanation for it other than the math makes it that way. It has to do with something called linear combination of atomic orbitals, but it's not something we need to worry about. In any case, if we think about what would happen if we subtracted the SB orbital from the SA orbital, let's try to draw the graph again and see how poorly I do this time. So remember, in red was our just 1s orbital by itself. If we were going to subtract the 1sb orbital from the 1sa orbital, we could first draw the opposite of the 1sb orbital. And, you know, if that were perfect, I would have gotten the magnitude correct. As it is, we'll just sort of hope for the best. Add these two together. What's going to happen? And let me just be clear. This is our 1sa orbital by itself. This is our 1sb orbital. What's going to happen there? If you add the two of them together, they should cancel out there. Just give me a little bit of plus minus, just a little bit of uncertainty on the drawings. I'm sorry, it's not perfect. Yeah, it's going to cancel out there in the middle. So if we were to draw what the new orbital would look like, it's got to go through 0 there. All right, and if I could maybe just switch back over to Dropbox and use my cursor, here, this tiny dotted line that you're seeing, that's, let's see, can I zoom in? No. That's the 1SA minus the 1SB. And you can see that at the peak, the slope starts to change even more rapidly, right? Because you not only, you can't just, because you've subtracted the one from the other, you've got to go through 0 and get to the whole other side of the amplitude right away. And so the second derivative of that subtracted combination is higher. And that means its kinetic energy is higher. So that orbital, that 1sa minus 1sb orbital, is actually higher in energy than the orbitals you started with. Okay? And you may not have thought very much about orbitals that get higher in energy than where you used to be. What would that look like conceptually if we were to think about bringing a 1s orbital from hydrogen A, and let's see, the 1s orbital from hydrogen B, bringing them together out of phase. Need to draw circles that are more consistent, don't I? It's kind of an ugly circle. you didn't know this was going to be an art class, and you didn't know that it was going to be an art class taught by someone with no artistic talent. So what are we going to do? But anyway, where they start to overlap out of phase, they cancel each other out. And you have a plane between the two sides where the wave function goes to 0. And again, because the second derivative of the wave function is higher at that point, its kinetic energy of the electron is higher, which means that this out of phase combination is going to be up here if this is an energy axis. Okay? So sometimes, and maybe you saw this in Gen Chem, maybe you didn't, we'll draw molecular orbital energy diagrams where we're basically showing the mixing of two atomic orbitals together. Down here you've got the plus combination or the constructive interference combination. That's always lower in energy than it was when you started, and because of that, we call it a bonding orbital. That's what holds the molecule together, but somewhere up there at a higher energy level, empty, but still there, is your minus combination, your destructive interference combination, the 1sa minus 1sb, and we're going to call this an antibonding orbital. Okay? Questions so far? Yeah?
The electrons can be in state both in the positive and negative state.
Yeah, so the question is, if I were hypothetically to populate this 1sa minus 1sb orbital, could an electron occupy both of those places at once? And the answer is yes, just like our slinky wave goes through 0 but nonetheless occupies both places at once. Okay? Doesn't make any sense if you think about the electron as being a little marble, but it makes sense if you think about it as being a wave. Okay? Incidentally, all particles have a wavelength. You can read about that in the introductory study guide, but that wavelength drops down really, really, really tiny once you get masses that are that much higher than an electron or a proton. So yes, you have wavelength, but it's too small for anybody to ever see or worry about. So sad for us. That's why we can't walk through walls or stuff. But weird. Sorry about that. That was a strange digression. Other questions? Wallace, how are we doing in the chat? Anything coming up yet?
No questions that we have.
Okay. All right. Now, one thing that's not immediately clear from the way we've described things, but it is a consequence of the MO theory math. If we sort of call this line where the atomic orbitals start out, this is sort of our break-even point. And if we measure the energy distance, the distance in energy between our bonding orbital and our break-even point, we'll call that delta E B for bonding. And then if we measure this distance between the antibonding orbital, delta E AB for antibonding, obviously delta EB is going to be negative and delta EAB is going to be positive. But if we just compare their magnitudes, we're going to see that the antibonding orbital is higher in energy relative to the break-even point than the bonding orbital is lower in energy, right? So, and this is a general feature of bonding in organic molecules. The bonding orbital is lower in energy, and that's what makes the bond form, but the empty antibonding orbital is not just as high above the line as the bonding orbital is below, but it's even higher. Okay? So let's talk about the consequences of that. What would happen then to my hydrogen molecule if I decided to take a photon of light precisely tuned to this overall energy difference. And if I were to bring it in, hit an electron, and then, this is the fun part that you guys can't do at home, protonate it, or I'm sorry, promote it to a higher energy level. What do you think that does to my molecule? Takes me past the break-even point, right? Now there's no benefit at all to having the two atoms that close together. In fact, it would be better for them to fall apart, right? This is why we call it an antibonding orbital, because if we put an electron in it, if we promote an electron from the bonding to the antibonding orbital, we are going to break the bond. Go ahead, Wallace.
Here's a question from the chat wondering why that one's always of greater magnitude.
Yeah, it's a good question. The question from the chat is, why is the antibonding orbital always higher in energy? Why is that delta EAB of greater magnitude? It actually comes from the math of MO theory. That is my cop-out, hand-wavy answer, but I actually do know the answer to it. It has to do with something called the overlap integral, and if you want to, and you assume that the overlap integral is not equal to 0, and then you do get that answer out. If you want to see the math, I can show you. It's in this book called Modern Physical Organic Chemistry by Anslin and Doherty. And if you want to learn more about that, you can take my Chem 552 class. But if you're afraid now, you should be even more afraid. I was so afraid when I had to teach this class, just barely in the fall. I had to learn so much, and I clearly don't get it all yet. So if I could just answer that for you folks at home, I sort of know, but it's too hard to explain, and you don't need to worry about it. Is that a decent enough answer? Okay, other questions? I guess similarly we could ask, we could use this same situation to, I'm trying to get the arrow down there. What would happen if I took 2 extra electrons from somewhere and dumped them into the antibonding orbital? Same thing, right? Yeah, I mean, it's effectively the same as promoting 1 electron. They would cancel each other out. And we're going to see that a lot of organic reactions that involve bonds breaking often involve one molecule dumping electrons into the antibonding orbital of another molecule, and that causes a change to happen. And we're also going to go blow the top off the whole octet rule or whatever. Remember how I said that hydrogen doesn't know about noble gas configurations? Do you remember that helium doesn't form bonds with itself? And we're learning that in general chemistry. Well, helium has the same 1s orbitals available to it as hydrogen does. The difference is, okay, the nucleus is positive, is +2 instead of +1. But the orbital should be the same. So let's imagine what happens. Pretend instead of hydrogens here, these are helium nuclei. How many valence electrons does helium have? 2. Okay, so if you tried to make helium He2, what's going to happen? Populate the antibonding orbital, and I'm sorry, there's just no benefit. In fact, it's worse. Okay? So that's actually the origin of that rule. If you've ever wondered, well, why does helium know that 2 electrons is special? No longer because they told you so. I mean, it's true, so it didn't matter whether or not they told you, it was still true. But the reason why is the electrons don't get any more stable if helium were to bond to itself, because you're going to make a bonding orbital and an antibonding orbital, and if you fill the antibonding orbital, you're done. All right. Now, in the last little bit, we're going to talk about applying this strategy to larger molecules. Okay? And we're going to start with the perhaps next simplest organic molecule that's neutral, and that is methane. Now, using valence bond theory as described in the introductory study guide, we know that methane is tetrahedral. We've talked about hybridization. Just a little bit of nomenclature, rather, drawing conventions. The wedge here means that hydrogen is coming out at you. The dash means that hydrogen is going back into the page. You must learn to see on the two-dimensional page a three-dimensional structure in your mind's eye. Right? You must, when you look at that, you must see, oh, all of those bond angles are 109.5 degrees, so that thing is tetrahedral. If you struggle with that, and frankly you should because you're new at this, you might want to go get a model set. Frankly, any of them on Amazon are probably fine. Just get one that's easy enough to use but not crazy expensive. And I have some models in my office if you want to come look at them and try to build molecules. But it might be useful, at least until you're good at looking at the page and seeing the 3D structure, it might be useful to work with a model set. What we're going to do next is we're going to explain the bonding in methane without using sp3 hybridized orbitals. Just going to use the alphabet of 2s and the 3 2p orbitals on carbon, and then a 1s orbital from each of the hydrogens. And that's the first time we'll really see how crazy molecular orbitals can be. You thought it was crazy this time, you ain't seen nothing yet. All right, so see you next time. Have a good afternoon.